Hello everyone, this is lecture 7 of PTRE 475575, well completions and advanced stimulation techniques. Like I said last time, there will be no lecture this Thursday and there will be no office hours. I will see if where we stand at the end of this lecture. If I do have to record one, it's gonna be done this weekend after I come back from Houston. I will see basically on where we need to be for the first homework, which I think it should be posted sometimes next week. Or I don't think we'll be able to do that before. Maybe we can do it at the end of this class, but by the end of this class. In that case, I will post it early so you can work over during the weekend, but most likely it's going to be posted early next week. There is also a chance that next Tuesday may need to be the lecture may start a little bit late, and then or it would be like a half lecture, and then because I have a lunch with an industry visitor, and I think the lunch ends at I don't know. In that case, I will definitely record a makeup lecture and upload it online. But I will let you know when the time comes. I don't know yet. But they are shooting for a lunch at 12 to 1:30. So if I have to go, I cannot leave early. I don't know. We'll see. Anyway, last time we went through the very important topic of near wellbore stresses. We said that when you have a wellbore, you basically remove rock, you replace it with fluid, and therefore you disturb the stress field surrounding the wellbore. So when you go near the wellbore, you don't have what you had before, like SV, SH max, SH min. You have a different set of stresses that are in cylindrical coordinates. They are called the near wellbore stresses, and those are affected both by the far field stresses, as we call them, SV, SH max, SH min, but also by things that go on inside the wellbore. And we talk about the long history of people trying to derive equations, even today, for different models about those. Basically, the same idea is started by people doing work in canons, for canons, and then slowly we moved to geology related settings. Hubbard and Willis, that were geologist people. They were geologists, and then Forshell, and then Heinsohn and Fairhurst, who were geomechanicists for University of Minnesota. And even today, I mean, even my students have their own equations, and you can add as much complexity on those as you like, but it gets mathematically very ugly. There was a student one of my graduate students that walked in the room towards the end of last lecture, and he's one working on this kind of stuff. His name is Nassim. He actually incorporates the presence of the wellbore as well. And then we saw those equations. We saw the Hubbard and Willis version of those equations, which is basically Kirsch with static pore pressure included. As if you have the pores, they are filled with fluid, but the fluid is not moving, staying there stationary. And it's already mathematically pretty ugly. And we did some simplification. We said, how does it look like when you're on the wellbore radius? That means R equals RW. All those fractions RW over R become 1. And then we said, okay, that simplifies the shear stress. It becomes 0. That means no shear on the wellbore, on the borehole walls, which is something I mentioned earlier that day. Then we went the other way. We went very far away from the wellbore. We did R much bigger than RW. So basically, those fractions become 0. And we saw something very interesting, is that when I'm looking at one angle, if I'm far from the wellbore, an angle equal to 0. So let's see. SH max. SH mean. If I'm looking here, and I'm far away from the well enough, the radial is the same as SH max. Well, the direction is gonna be this way. But doesn't make much of a difference. Then the tangential, well, it makes a difference, like if it's compressive or tensile, it's gonna be compressive in that case, but yeah, I care more about the direction, the orientation in space right now than the arrow. Now I have also the red is gonna be parallel to SH mean. So sigma theta theta becomes the same as SH mean, far away enough at angle theta equals 0. Let's see, and the axial is the same inside the plane of the paper. And this is, remember, theta equals 0. Now at theta equals 90, so if I come here far away from the wellbore, trying to find the stresses at this point, look, the radial is parallel to SH mean, so it's SH mean if you are far away enough from the wellbore. The hoop is what? SH max, because it's parallel to this. And of course, axial is into or out of the plane of the paper, of the screen. This one. Sigma ZZ. And we call it sigma ZZ because we assume that the well is very parallel to the Z-axis. If it's very parallel to the X-axis, like Nassim is doing, because he's interested about horizontal wells, it would be sigma XX. When I was a PhD student, I was setting my wells parallel to the Y-axis. So the axial stress was called sigma YY. It's the same thing. I think in geomechanics, you saw some exercises that were sigma II. Same thing. Whatever you call that axis to be in cylindrical coordinates. Remember, in cylindrical coordinates, you have only one linear axis, and generally it's called Z. The other one is theta, and the other one is, in fact, you have two. R and Z are linear, and then the R is rotating. This is what I say here, and what I say here, the same thing. Go away from the well at theta equals 0, because theta equals 0 is along SH max. The radial stress is equal to SH max. The tangential stress is equal to SH mean, and vice versa for theta equals 90. And this is what the plots here are showing. Now, those plots were not made by me, so they were not honoring the color scheme I use in all my classes and all my publications, that has the sigmas, the axial always blue, tangential always red, radial always green. And of course, in these plots, we also don't see the shear stresses yet. They are important. They are important. Okay, so now we are going to shift gears a bit, and we are going to talk about fractures. And you understand why we are doing that, because fractures are related directly to the local stress state. People like the student Nassim, when they model fracture initiation, they don't model the actual fracture initiation. They model how the stress field changes in the body that they are modeling. The wellbore with the intersection to the perforation, for instance. And when the stress overcomes some thresholds, he says a fracture has started. It's in this orientation, and it started at this time when the wellbore was pressurized at this pressure. This is what they are doing. And another student I used to have, Hakim, who was doing work on fractures after blowouts. This is the same thing that they are doing. They are not modeling the actual fracture movement. They model the stress field and they say, aha, now I satisfy the conditions required for those fractures. But those fractures are what we call tensile fractures, or what more scientific name for them is mode 1, opening mode fracture. And these are until Albert and Willis' paper of 1957 came out, people were arguing with each other whether the fractures are always horizontal or always vertical. And they all had evidence for what they were suggesting. And they were all holding strong beliefs because they had strong evidence about drilling well, fracturing it. They were vertical wells back then, but they were getting vertical fractures or horizontal fractures. And they had strong opinions. Now, in 1957, Hubbard derived those equations and then used those equations to explain that fractures are not always horizontal or always vertical. They can be either horizontal or either vertical. It depends on the local stress state. And he explained that very well in what probably is the best paper in SPE's electronic library, electronic paper library, the Juan Pedro. Certainly the best one from the previous century. The important point about that is something that you guys learned in geomechanics when you are doing the same topic. The fractures, mode 1 fractures, opening mode, always open against the least compressive or more tensile stress. And we say S3, okay? It can be SH mean. If you are in a normal faulting stress state, it can be SV. If you are in a reverse faulting stress state or a strike slip faulting stress state, if you are near a wellbore, it would be either sigma theta theta, sigma ZZ, sigma RR, whichever of the three is the least compressive, most tensile. And it's basically natural. The Earth, the nature wants to do the least amount of work. It wants to input the least amount of energy, and this is what happens. 1 second. Am I sharing the right screen? Yes. Am I recording? Yes. If there's any questions, feel free to, don't put it on the chat, just feel free to speak up, because if I'm standing in front of the podium, I don't really see the, now I do see, but if I'm standing in front, I do not see what is on the screen. What is on the second screen? The other screen, the one that you guys are seeing, I'm seeing it too on the projector, but no reason to push away rock in a direction of higher stress if there is another direction in which the stress is lower and it's easier to push. It's like electricity, it always takes the easiest path downwards. In this case, the fracture will open in the direction that requires the least stress. And because it's opening mode, it should be perpendicular to that. So I'm opening against that least compressive stress. Therefore, tensile fractures will be perpendicular to the least principal stress as long as this S3 is less compressive than S1 and S2. So it needs to be less compressive. By definition, S3 is less compressive than S1 and S2. If S1 or S2 was the least compressive, we would be calling that one the S3. In purely triaxially loaded stress environments, a tensile mode 1 fracture opens in the direction of S3, propagates on the plane, in the plane S1 and S2, or in the plane perpendicular to S3. I know the vernacular here is a little bit confusing, and it was confusing for me when I was young. I will try to explain it a little bit better. This is why horizontal wells are drilled parallel to SH mean. Presence of wellbore and perforations can impact the stress state in their proximity. Okay, let's take that step at a time. So I have a page here from somebody left it. This is a fracture. Okay, it's a page. It has length, it has height, and it has width. When we say a fracture opens, we are talking about the width of the fracture, the smallest dimension of the fracture. So the width of the fracture is the direction the fracture opens. If it opens more, it becomes fatter, so bigger width. Okay, so this here, across the direction across its width, is the one that where the stress needs to be least compressed. Okay, across its width. And then you are left with two more dimensions. A big one, let's call that the length, and the height. Okay, in that case, you have S1 and S2. The bigger of the two dimensions is going to be S2. So in this case, the length is S2. Okay, the height is S1. Now, if it was like this, the width remains S3, but it's more tall than long, the fracture. So the height is bigger than the length. So S2 will be in height and S1 would be in length. So I'll leave it. Imagine the fracture a little bit like a 3D thing. So I hope I do a good job drawing this. It's not easy. And make it more pronounced. Okay, what is the shortest dimension? It's basically this one, the width. So this is S3. Always, 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 the width is the one that is opening. This is the work that you are doing when you are pumping fluid downhole to open a fracture, is to open the width of the fracture. It's the most important dimension. And then you have two more. You have the height and you have the length, or the half length, as we are going to learn to call later on. Okay, whichever of those two is the bigger, it's basically S2. So this is the S2 direction, and this is the S1 direction. And obviously this is S3, the width. Now, imagine if I have a fracture that is like this. And I'm exaggerating a little bit, of course. All right. Width, the same. This is S3. Height, length. Obviously, this fracture is longer than height, so the length is S2. The height is S1, the strongest. And then same thing as I did with the paper, the page, the piece of paper that I was holding earlier. Now, why do we drill wells parallel to SH mean? It's the normal sort of a rule of thumb. Drill the wells parallel to SH mean. This is the way you're gonna get the fractures the way that you want them to get them. Otherwise, you won't. So why do you do that? You do that because, in fact, in Louisiana, it's a state law. You have to drill your well in the north-south direction or the southwest, I guess, direction. So you either drill them like this or you drill them like this. And if you drill them like this, it's parallel to SH mean towards the Gulf. Why do I want to drill my well parallel to SV, SH max, SH mean? So why is the well parallel to SH mean? If it's a normal faulting stress state, which is the most likely, the fracture will open against this SH mean. So the width of the fracture will be parallel to SH mean. And it will be propagating perpendicular to this. So it will propagate in the plane of SH max and SH mean. So the fractures I'm gonna get are gonna be intersecting the well bore, what we call transversely, which is for the, it's gonna be like this, fractures. For the non-native speakers, transverse means orthogonal, which means perpendicular. It cuts, let's use the page. This is the well bore. The fractures are like this. So I can fit 1, 2, 3, 4, 5, 6, as many as I can along the lateral. Okay? This is the way that I would like, ideally, the result of my frac job to be. A lot of fractures transversely, parallel to each other, as many as I can, stacked next to each other, as close as I can put them the better, blah, 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 blah. This is the goal. So, to maximize my chances for that, I will drill my well bore parallel to SH mean if I'm having a normal faulting or strike slip faulting stress state. By the way, earlier in class, I said that in strike slip, the least compressive is SV. I was wrong. It's SH mean as well. It's ironic because when I go to Houston this week, I'm gonna give a presentation on how to get fractures like this in reverse faulting stress state, where the S3 is SV, which is actually your TA's master's project. We will try to ultimately get a patent out of that situation. But yeah, back to what we are talking about is that, yeah, if I have normal faulting or strike slip faulting, and I apologize for the earlier error when I misspoke, it's you really want to drill your well parallel to SH mean. If you have a reverse faulting, you need to do something more exotic to do that, to get that. Now, the presence of the well bore itself, as we said earlier, impacts the stress field surrounding it. So many times you may drill the well parallel to SH mean. It might not be enough to do the job for you. It might be that the disturbance of the stress field near the wellbore, because of the presence of the wellbore and all the complexity associated by it, it disturbs the stress field so much that it does not lead to what you expected, the result that you expected. So we said it's a rule of thumb, but it's not set in stone, you know? It's not a set in stone thing. It doesn't mean that if I drill the well correctly, everything else will follow correctly. So there is impact of near wellbore stress interference on fracture initiation. And like I said, drilling the well parallel to SH mean is not enough. When I'm near the wellbore, it's no longer SH mean, SH max, SV. It's sigma ZZ, sigma RR, sigma theta theta. So these are the stresses I need to be worrying about. Big implications from the interference due to the presence of the wellbore in well completions and stimulations. So you need to take that seriously, this stress interference. I took this picture from the book, Hydraulic Fracture Mechanics, that I suggested for this class by Valco and Economidis, which is very, very useful book. When I was young in Texas, hydraulic fracture design was taught by Mark McClure, who is now he went on his own. He founded ResFrac, which is the most technologically advanced fracture simulation company. They don't do just fractures, they also do fluid flow through them. They do geomechanics and reservoir modeling in one simulation. And it was a startup, but now it's a very big company, and he has been hiring a lot of very smart people to work for him. He hires big names, you know, big names. He was a professor, like 27, 28 years old, back in Texas. I never took a class from him, but I knew him. 2 summers ago, when I was driving to Oregon, I was in California, driving through Oregon, and I was going to pass from San Francisco. I sent him a message, and we met for a coffee on my way north. Yeah, very, very nice person, very good guy, and very, very smart. So causes hydraulic fractures often to initiate in a plane different than the final propagation plane. On the top picture, figure 4.6 is what you are going after. You drill your well parallel to a SH mean or sigma H mean, as he calls it. Valco and Economidis call it in this diagram, and you get the fractures that are transverse, as I showed earlier on my hand. Transverse. This was the goal. This is what I got. End of story. I'm happy. Now, at the bottom, I had this interference that was significant. And what happened, it changed the stress field so much in the near wellbore region that the fracture did not initiate transversely. It initiated the wrong way. It initiated longitudinally. And then, as it was leaving away from the wellbore, it was forced to twist to the right direction, because as I was moving far from the wellbore, the near wellbore interference, the interference from the wellbore was diminishing, and the fractures, there was a force on the fracture to reorient to the right direction. So I always use blue for transverse and red for longitudinal. So on the top figure, I'm good. I'm good with what I have. All blue. All blue. At the bottom figure, I started red. And then I twisted. It was forced to twist to become blue. This twisting is very bad. Production-wise, it creates like a choke effect on the fluid, both production-wise and completion-wise. It restricts propane to move and gives what we call screen out when you do a completion, when you do a stimulation treatment. Now, every time you pump a stage, a frac stage, when you go to the field, and we're going to talk about it more in module 3, most of the stimulation stages, they end up with a screen out, okay? You hit a situation where the pressure shoots up on the surface. You are pumping as hard as you can pump, but the pressure is not really transmitted downhole because there is an obstacle to the flow. And the obstacle to the flow is sometimes created naturally. You want it to be created when the fractions have grown enough, sufficiently. You don't want it to be created as soon as you start pumping early on. And this twisting can be the cause of early screen out. And also, when you are producing the well, you flow the other way, you may end up in a situation where the flow is obstructed by a twisting. So you get a well that is not stimulated the way that you wanted, and then it's not producing the way you are hoping. You get two types of problems. This is not good, along other stuff, along other problems, like stage communication, fluid from one stage moving to another, and so on and so forth. So if you want to build a nice model, you need to include what happens in the near wellbore vicinity. And it's very hard to do so. There is so much complexity. Even people like Nassim who write complicated models in different software, there is so much complexity that it can incorporate. I mean, there's so much detail in the shape of the well, etc., that you don't really, you can never have a model that is 100% representative. It would take months to run. Okay. So the magic, the key to answering these questions is having we can do it mathematically at the detail level that is like pretty elementary. And then the more complicated it becomes, you end up getting to a point where you can no longer do it mathematically, you need to do it computationally. You cannot still solve a few equations, you need to solve something like 1,000 equations or something at the same time. So in this class, we are going to stay at analytical level, which is like mathematical. Mathematical means A plus B equals to C minus D. Computational means matrices, a lot of equations solved at the same time for many unknowns. We don't have a computational component in this class. That will entail writing your own code, which is it's basically doing what you do at the reservoir simulation, but with your own code and not for pressure and saturation as you do in reservoir simulation, but for stress and strain. Okay. Now for a vertical well, I took the equations from earlier and I said R equals RW. So I simplified the equations to these expressions, which are pretty simple. None of them takes more than one line. And they're fairly nice. Remember, theta is the clockwise angle from 90 degrees, from 0 degrees from the top, which is from the SH max. And these are Hubbard and Willis equations. They assume assume pore pressure, static pore pressure. Now, shall I say it now or? Okay, let's switch now to horizontal well. So there is several ways you can do the transformation. I want to move from vertical well, sigma ZZ along the Z-axis, to a horizontal well. There is several ways you can mathematically manipulate the equations for that. What I do, I don't know if it's easy for me, but I don't know if it's easy to learn. But what I do is that I replace SH max to SV. So now I measure theta not clockwise from SH max, clockwise from SV, provided that the well is drilled parallel to SH mean. So SV becomes SH mean, SH max becomes SV, and SH mean becomes SH max. And this way, and the well bore is assigned to whatever axis I would like it to be. In this case, it would be the y-axis. So the equations become like this. And that is with variable r. I can simplify them by setting r equals rw or r much bigger than rw. One thing to note is that the well is drilled parallel to SH mean, and the angle is clockwise from SH max. This used to be SV, is now SH mean, and everything else switched. Like SV became SH mean, SH max became SV, SH mean became SH max. That's one way of doing it. There is other ways you can do it, but you may be more complicated and you will need trigonometric functions if the theta changes. That's what I used to do when I was young for my research. I think it was easier. Very easy to change this sigma y to x. If I say this is x, this will become sigma xx. Very simple. Now, let me simplify those for r equals on the wellbore radius. Just take the equations, set r equals to rw, and you have these clean lines. Now, imagine looking at the wellbore from the side. And this is a horizontal wellbore, drilled parallel to the y-axis. I'm looking at it from the side. This is the y-axis. Z on top, X. So Z and X is coming out of the screen towards me, facing the screen. Okay. Now, that's why I told you that I don't really care about the arrow direction of the stresses. I care about their configuration in space. And I'm going to ask you, if I'm looking at the wellbore, this is the wellbore, it's like this. I'm looking at it from here. What is the direction of the stresses that I'm looking at? It will be, this will be the axial stress, sigma y. This the hoop stress, sigma theta theta, and out of the screen towards me is the sigma RR. Coming out of the screen towards me. And I drew the arrows a little bit, they should be the other way, but it should be like this. Sigma ZZ. It should be sigma theta theta, and it should be sigma r coming out of the screen. Now it's hard to understand very well, but what I'm trying to say is that if a fracture opens against sigma theta theta, it will be a fracture that is like this. So the well bore is like this, the fracture would be like this. And what we call this fracture, remember, I'm opening, the width is against sigma theta theta. Okay? So the fracture is like this and coming out of the screen of the out of the screen. So like this, not like this, like this. What is this fracture called? The answer is longitudinal fracture. So if the S3 was sigma theta theta, I would get a longitudinal fracture. Like this is the well bore, the fracture flat, like a pancake. Okay, all around the well. What if the I made a mistake here. Radial is sigma yy. It's a horizontal well. What if the fracture? What if S3 was sigma yy, the axial stress? It would be a fracture like this, a transverse fracture. So the dynamic, it's a fracture. The well is like this, the fracture is like this, or like this. Still transverse. Still transverse. So I'll be good. That means I need to look at both stresses, sigma theta theta and sigma yy. And the tensile fracture from there is the case. Now, somebody may ask, what if it's opening again? What if sigma 3 is S3? Sigma 3 is radial stress, sigma RR, the green. What is going to happen? Is it possible? The answer is yes. And what is going to happen is like the side of the well will peel out of the well. It's called debonding, okay? It's a very common problem faced with cement jobs. They are they are detached from the casing and the well bore, and they create what we call microannulus, and that is by the radial stress. Before, I think we can do that. Shall we? Well, no need for that. We'll do it another time. But well, actually, you will need it for the homework. So I hope it's not confusing. If it's confusing, ignore what I'm gonna say for now. But it's gonna come into play. The criterion, mathematical expression. When we hear criterion in sciences, hard sciences, think about the mathematical equation. For this mode 1 fracture to occur is that S3 or sigma 3 should, no, let's not use that, become more tensile than the tensile strength of the rock. So if the tensile strength of the rock given by T, capital T, is minus T, because, and I'm putting minus because of my convention, tensile stresses are negative. This S3, whether it is sigma RR, sigma theta theta, sigma YY, needs to become more tensile than the tensile strength of the rock. So if this is the case, I get longitudinal fracture initiating, right? That's why it's colored red. If this is the case, I get transverse fracture initiating. That's why it's colored blue. This is the case, I get debonding. Don't worry about it now. Now, it's not enough for this to be the case to get transverse fractures. Okay, it's not enough. Why is it not enough? Because one of the other two may have satisfied. What happened to the T on the top? One of the other two may have satisfied this condition earlier, which is not good. It means that, yes, I may be like this, but it doesn't mean I'm going to get transverse fractures. I may already have longitudinal fractures. I may already have debonding. So that's what I am saying. The tensile failure criterion, think about it like in Moore Coulomb, what we said in Moore Coulomb, it was a criterion that we saw, but it was for shear failure, shear compressive failure. Now we are seeing the criterion for the tensile failure, which is actually much simpler than Moore Coulomb, which itself is simple enough. Shear stress equal to 0 on the well bore. Any questions before I shift gears to a different subtopic?
Oh, so thank you.
Okay. Not very different subtopic, quite related. Borehole stability, which you should have already seen in geomechanics, is very similar. We talked about tension and we talked about compression, shear compression. Two types of failures. Like mode 1 is tension, hydraulic fractures, etc., etc. Mode 2 is, and mode 3 are compression, shear failures. When I'm drilling a well bore, it's impossible to have the specific exact mud weight every time. I drill it, I get little bit of failure. You know, we learned in drilling that when you drill a well bore, you need to be between higher than the pore pressure, lower than the fracture pressure. You need to be in between. And the examples that we gave are pretty big windows, wide windows, etc., etc. Now, this is not always the case. You're always having a little bit of an error. It's just like when you are driving, you don't know it, but you make so many corrections when you are driving. I don't think anybody woke up in the morning and turned the string, came to school from their house and they didn't make a single correction while driving, right? There is a point where you turn the steering wheel a little bit further, bigger angle than what you had to release it a little bit. You had to, maybe you didn't turn it well enough. You had to turn it a little bit more. You constantly make these small corrections. Now, if you lose the car on the snow, you will have to make a big correction. But it's the same idea, okay? Now, these small corrections are being recorded on the walls of the well, okay? When you had too small of a mud weight, you get shear failures, and this is what we call wellbore breakout or wellbore washout, etc., etc. And when you have wellbore pressure too high, you get what we call drilling-induced tensile fractures. Okay, drilling-induced tensile fractures, we call them in this diagram. They call it induced fracture. DITF, drilling-induced tensile fracture, is basically mode 1 fracture, and it's the same DNA as the hydraulic fracture that you are doing in stimulation. And it's the same DNA as the underground blowouts that we learn to be afraid of in drilling. Same thing, same exact DNA. If you are trying to model them mathematically, you are going to do it the same way. You are going to use that tensile failure criterion I mentioned earlier in the previous slide. Now, wellbore breakout is basically, think about it like we are saying in drilling when you get a kick. That happens before getting a kick. It's an earlier threshold. When you drill a wellbore and chunks in the minimum direction, in the direction of the least compressive stress, are removed from the walls. So the opening, the hole, looks elliptical. And people are using the direction of the borehole breakouts to tell you, if it's a vertical section and the ellipse is like the one I drew, the long direction where you see the let's not draw it with, these are the breakout zones. Like, this is the breakout zones. I think the proper way to draw it is that it was fully circular, and now it's more these long directions are the breakouts, and it indicates, what am I doing? The direction of SH mean if it's a vertical well. Or if it's a horizontal section and you have SB on top and either SH max or SH min on the side, the direction of the breakout is the direction of the least compressive of the two, relatively least compressive of the two.
Professor, is this related to the safety margin?
Safety module?
Safety margin of the mudway?
Yes.
Yes. Okay.
Yes. Yes, very good question. If you are going to use the breakout pressures, it would be the left side of the mud window, where we are putting pore pressure when we are doing drilling. This is a higher limit. This is a higher limit. It shifts the left side to the right, closes, makes the mud window more narrow. Very good question. Now, if this is a vertical section, we're going to have, this will be SH max, which is by definition bigger than SH min. And I'm going to have drilling-induced tensile fractures in this direction. It's going to look like this. And why are they in this direction? Because of something that we talked about earlier today. They are hydraulic fractures. So they are weights. They are opening against the least compressive of the stresses. That means they are opening, doing work against S3, which in this case is SH min. If it's a vertical section, it's going to be between SH max and SH min, and SH max is always bigger than SH min, more compressive. So that makes this, if you're in a horizontal section, it's more complicated. It's more complicated. Now, they both appear on something called image logs. Both drilling-induced tensile fractures and what's the other? Wellbore breakouts. They have a different signature. And when you see an image log, initially, it looks confusing. But once you train your eyes to look at to recognize what you are seeing, it's going to be much easier. Okay, I promise. It's going to be, with experienced people, you show them the image log from far away and they tell you where is is the direction of SH max, and what is the azimuth of SH mean, etc., etc. There are people that are very, very advanced in reading image logs. It's a powerful tool in terms of diagnostics. And you are going to see in homework one example where the valuable information is extracted from the image log. So the more adept you become at it, the better. Borehole breakouts occur along the direction of the least compressive stress, along the wellbore's cross-section, along the SH mean direction in vertical wells, and then drilling induced tensile fractures initiate orthogonally to breakouts along the direction, SH max direction in vertical wells. Vertical wells are easier in this case to worry about. And this is a picture from PTRE. Before the website became very hard to navigate through now, because I think they merged SP, merged PTRE with one Petro, and now I really don't know how to do it, how to navigate through. But this used to be a page I spent a lot of time in. It was called Elastic Stress Concentrations Around the Wellbore. And it shows how the two important stresses, hoop, the tangential, and the axial, are varying around the wellbore. You have the axial, and you have the tangential. And then here, with the black line, you have 0, which is basically the tensile strength of the rock, assumed to be 0. Now, remember what I said earlier. To get a fracture to form, you need to satisfy not just one condition, okay? You need one of your stresses to be more compressive than the tensile strength of the rock, and the other stress to be more compressive, more tensile than the other. Sorry, I said it wrong. The stress needs to be more tensile than the tensile strength of the rock, and one of the stresses needs to be more tensile. That same stress needs to be more tensile than any other stress. So in this case, we get fractures, drilling induced tensile fractures. Let me use red, it's important. The wellbore is vertical, and look at the direction of the stresses. Are they longitudinal or transverse to the wellbore? And the answer is they are like this, they are longitudinal. It's like the schematic in the nice 3D schematic from the previous slide, which suggests to me that sigma theta theta is more tensile than the tensile strength of the rock, and also more tensile than the ZZ, the axial. How will that be interpreted in the diagram is what we see on the right. In this small angle range that I will indicate with orange color, what happens here is that those two conditions are satisfied. And you have those drilling induced tensile fractures at this narrow angle range. Very, very nice. This is how you interpret the image log. If I got an image log, and don't worry how the image log looks like for now, we're gonna get to it. And I saw longitudinal drilling-induced tensile fractures, I'm expecting something like that. If I go transverse would be a little bit weird. Yeah, I want to clean it. Transverse are rare, which makes it even more valuable. And they would be like, if the wellbore is like this, the fracture is like this. So it's going to be cutting, the image log would be cutting, the drilling-induced tensile fracture would be cutting the wellbore on the image log. It's going to look a different way. In that case, the other way, the criterion would be like this. The axial stress is more tensile than the tensile strength of the rock, and also more tensile than the tangential stress at that point. It may be that both are more tensile than the tensile strength of the rock. In that case, you care which one is the most tensile. Or from a real world perspective, which one became more tensile first? Which one satisfied the condition first? Because once you have one fracture opening, again, the stress field gets disturbed. So those equations may no longer be valid. So DITFs are the same as hydraulic fractures, same thing. Not many people know that actually, which is surprising. This is the criteria that needs to be followed. And what we can do, wait. We can come back to this equation for the stresses on the vertical well. And remember, we said the criterion is this. No, I want to make it black. This is the criterion I need to satisfy. Okay. Well, one of the two criteria. The other one is that this is more tensile than this. But let's just say, take the first criterion and set it on the limit. So say it equal to minus t. And then do something. Set PW and solve for PW, okay? You're gonna get an expression for the wellbore pressure at which these drilling-induced tensile fractures occur. Okay, you are gonna get basically a fracture initiation pressure indication, which we said it's very, very hard to get because fracture initiation pressure can vary from leak-off pressure to formation breakdown pressure. Now, once I do that, oh, look at this is how a longitudinal fracture looks like. Look, this is a longitudinal drilling-induced tensile fracture. If it was transverse, it would be like this, coming out of in this way. But the idea here is that, sorry, this is a horizontal well, I want a vertical well. Yeah, so this is where I was before. I did equal to t minus t. And I solve for PW. Now a question is, can I do the same thing for the transverse fractions? Can I do this for the blue, the transverse fraction? I can set the blue equal to minus t. And then where is the PW? I don't see any PW to solve for. So I cannot do it just because of the way those equations are derived. So I'm a little bit unlucky. The equation is too simple. It doesn't have PW for me. So I can either use a more complicated model version of those equations where PW is present and there is those. If you include poor elasticity, etc., if you make it complicated enough, that's what Nassim is doing, you have PW. If you don't, you still don't have. You cannot do what you did. You can do, or you can say the fracture is longitudinal and use this, which is an idea. Many people, many fracture simulation people, many modelers, they do that. They assume that the fracture initiates longitudinally. Or some of them, they ignore the presence of the wellbore completely, and they say, let me just say that it opens against SH mean, as if the wellbore is not there. There is no impact from the presence of the wellbore. So basically, I say PW is equal to SH mean minus PP. Very easy. But then again, it's a simplified model. Okay, now back to where I was. And I said, what I'm saying here is what I did. I basically said the expression of minus equal to minus t, and then I solve for PW. And we call PW FIP. And then I rearrange for SH max. And what I got is a version of an equation that I have seen before. We have talked about before in earlier slides. And if I remember well, I told you, we will see how this equation is derived later on. And that's how it is. This is what I meant. We went full circle and showed, so this equation here is basically the equation on slide 25 here. And this is how it's derived. We just go to, what is it, slide, you go to slide, what is it, 42. You said the tangential stress equals to minus t, and you solve for PW. Okay, so, and of course, this is only applicable to longitudinal drilling into tensile fractures, most common compared to transverse. Transverse is rare from the vertical well. It's not unrare from a horizontal well, but now we have time for an example problem. Example problem number 6. Data collected from a vertical well suggests LOP equal to 4,200 psi, that's the legal pressure, and FPP formation breakdown pressure equal to 6,900 psi. And geological survey suggests that the overburden stress at the casing shoe is 11,300, while the ISIP is 5,700 psi. The formation pore pressure is estimated at 3,300 psi, and the rock's tensile strength is 1,000 psi. Use this information to provide a range for the local SH max magnitude. What is the local in situ stress regime? Oh my God, what a complicated multi-component question. Reminds me of my former girlfriend. But anyway, you have a lot of, we have a lot of numbers and a lot of two questions to answer. But one question has two answers. We need to provide a range, constrain the range of the local SH max magnitude. So we need to find an upper bound and a lower bound. And then based on those values, understand what kind of in situ stress regime we have, normal, reverse, strike, slip, etc., etc. So let's gather the data. I have SV, which is the overburden. I have SH mean, 5,700 psi. I have PP, pore pressure, 3,300 psi. I have T, which is 1,000 psi. And then I have LOP, which is 4,200 psi, leak of pressure, and FBP, which is 6,900 psi. Now, as you remember earlier, I said FIP is between LOP and FBP. So any point between those, that's the range for FIP. And that's the range I'm going to apply. It's a pretty big range. It's like 1,700 psi. But those were made up values. It's not unlikely, but it's pretty wide range, I would say. So how do I solve it? Very easy. I use that equation. And for FIP, I use those two limits. LOP to get the upper bound of SH max, 3 SH mean minus LOP minus PP plus T. I get something 10,000 and a half, 10,600 psi. And then I get the lower bound by using FBP for FIP, which is 7,900 psi. Again, quite a big range. SH max can be as low as less than 8,000 and bigger than 10,000, which is more than 20% difference. The margin is like over 20%. It's very, very uncertain. But because I said earlier that SV is, what is SV? SV is 11,300. SH mean is 57. The range stays within the bounds of SV and SH mean. So for sure, the in situ stress regime is normal for me. So no problems. Just an application. It's actually simpler than the problem we thought. And I think we should call it. There is a video here for somebody doing experiments on gelatin, and he goes shallow, where the SV is small, and he gets a fraction that is transverse to the well. The well is the straw. He goes into a gelatin mix and tries to pump juice, something colored that you can see well. And the fracture, when you are shallow, is flat, is transverse to the straw. And then he goes deeper, more gelatin weight above it, and the fracture rotates to longitudinal. I have shown it in other classes as well of mine, like advanced drilling and geomechanics. But we are gonna see it next time, along with some pictures of image logs. And I think we are almost ready for the first homework. Let's see, I can already post it, but technically I just want to go through the remainder of the slides, but I can post it maybe, let's see. I can post it early so that you get more time to it. It also depends what we're going to do with the class on Tuesday. If I have to cancel that class and record it, anyway. maybe it's better if I post the homework early so you have more time to work on it. But anyway, no rush on this stuff. Thank you very much. Have a nice weekend. Remember, no office hours tomorrow and no class on Thursday, but I'm available via email. Same thing as the TA as well. So anything that you have, any issue, any questions, concerns, let us know and we'll try to address it. Thank you very much. Have a nice weekend.
Thank you, Professor.
Mm-hmm.